Section 5.3, Day 1, Riemann sums. We've spent the past few days approximating area under a curve with rectangles and other geometric shapes. Some methods are easier to use while others are more accurate. How confident can we be that our approximations are nearing the true area? The graph of cosine of x on the interval from 0 to 2 is shown. We're going to use right Riemann sum, so right rectangles, right endpoints, with 4 subintervals to approximate the area under the curve over the interval from 0 to 2. So how wide should each rectangle be? Well, if we're going from 0 to 2, and we have 4 subintervals, we'll take 2 minus 0 divided by our 4 subintervals, so they're each going to be a width of 1/2. I'd like you to pause the video and draw those 4 rectangles, and then use your work to approximate the area under the curve. So there's the picture of each of my rectangles. So now remember to figure out the area of each of those rectangles. Well, the width of the first rectangle is 1/2, and the height of the first rectangle is the cosine of 1/2. Second rectangle, again, the width is 1/2 times the cosine of 1, plus the width is 1/2 times the cosine of 1/2, plus the width is 1 times the height of the cosine of 2. Now let's figure out the value of each of those. Notice that this fourth rectangle has a negative area because it's below the x-axis. If we then add all these up, we get 0.5363 as our approximation. We introduce a new way to write this, new notation. This is the sum from I equals the first rectangle to the fourth rectangle of the height of each rectangle, that's an f of x sub I, times delta x. So that's just kind of a new notation. We're adding up the summation notation. We're adding up the first to the fourth rectangle of this is the height, and that's going to be the width. Do you think this is a good approximation? And explain. Well, I would say no, because we have all this area up here, all this area that's being unaccounted for. So it's not a very good approximation. All right, let's see if we can get a better approximation if we use 8 rectangles. How wide should our rectangles be now? Well, we're still using the interval from 0 to 2, but now we're going to have 8 rectangles. So the width of each rectangle is going to be 1/4 of a unit. Again, I'd like you to draw those and see if you can approximate the area under the curve. This is approximately what our rectangles should look like. Now let's go ahead and find the volume or the area of each of those rectangles. Writing out each of my widths times each of my heights. Using 8 rectangles, we find that the area is 0.7275. And again, showing you this new notation, this is the sum of the first rectangle to the 8th rectangle of f of x sub I times my delta x. Do you think this is a good approximation? Well, it's obviously better than the 4 rectangles. If I look at the unincluded area, there's much less unincluded area, and there's actually much less negative area as well. So it's better than 4 rectangles, but there's still quite a bit of space there. So now, given the 2 approximation, what is your best guess of the true area under the curve over this interval? I want you to pause the video and write that down. And then I'd also like you to do number 5. How many rectangles would you need to make a confident guess? And write your answer down for that one. And here are 4 examples of an increasing number of rectangles for that same function, the cosine of x. Here we have 12 rectangles. And here you notice 20 rectangles is getting to be a little bit closer of an approximation. Here are 50 rectangles. You can almost not even see any space. And here with 100, it looks like we pretty much have an exact approximation. So as the number of rectangles increases, what's happening to the width of each of those rectangles? You'll notice that the width gets smaller and smaller. It gets skinnier. My delta x is approaching 0. The width of each of my rectangles is approaching 0. It's never going to actually get to 0, but it can approach 0. So using this new information given, now what is your best guess as to the true area under the curve? Pause the video and see if you can give me a new estimate. And then how many rectangles would be needed to get the exact area under the curve over this interval? You might at this point be guessing that we need an infinitely many rectangles. Using our notation, we're going to have the limit as n approaches infinity of the number of rectangles from 1 to n. And again, we still have the height of each rectangle times the width of each rectangle. And this would involve the limit definition of the integral, as I mentioned to you before. This is going to transform into, we're looking for the area between the interval 0 to 2 of f of x dx. And we're going to learn how to do this, but I'm going to tell you that the exact area under this curve is 0.909. The decimal does go on, but rounded to 3 decimal places, the exact area would be 0.909. How many people had something very close to that? We are beginning to get to the crux of integral calculus. To find an exact area under a curve f of x over the interval a to b, we're going to use infinitely many rectangles of an infinitesimally small widths. The limit definition or summation notation for this is the limit as n approaches infinity. We're going to have the sum from 1 to n rectangles of the function f of x sub I times delta x. Now what's important here is that this n is going to be the number of rectangles that we're going to have. N approaches infinity. We're going to have an infinite number of rectangles. What we've been doing all along, this f of x sub I, this is going to be the height of the ith rectangle. Whichever rectangle or interval you're dealing with. And this delta x is going to be the width of each rectangle. And we're choosing a standard width, so our delta x has been the same, but h, or the f of x, is going to be when we plug whatever that value is in for our function. And we're going to start using our integral notation. This is the integral from a to b of f of x dx. Now remember that we're in the interval a to b, so this a is considered our lower limit of integration, and the b is our upper limit of integration. The f of x, similar to in our summation notation, but this is now called our integrand. And our d of x is telling us the variable of integration. This is telling us which variable we're actually taking the integral of. Make sure we understand what all this means. Number 1, snow starts falling at 6 a.m. The rate that snow is falling overnight is represented by the equation s prime of t, where s prime of t is measured in inches per hour, and t represents hours since midnight. Write an integral expression that gives the total amount of snow that falls during the first 3 hours of the snowfall. Well, t is representing the hours since midnight, so we're looking at the first 3 hours of snowfall, which starts at 6. Therefore, it would go to 9. And we want the accumulation of snowfall, so that's going to be my function, and it's going to be with respect to t. Number 2, the function c prime of t gives the rate in bars per minute at which chocolate bars are being removed from a shelf at the grocery store, where t is measured in minutes. Using correct units, interpret the meaning of the following expression in the context of this problem. Well, from 0 to 9, so we're talking about during the first 9 minutes. What was the accumulation? Well, there was a total of 46 chocolate bars that were removed from the grocery store shelf. In the midst of this coronavirus quarantine, it might have been more appropriate to change those chocolate bars to toilet paper, huh? Okay, number 3. Paula's using rectangles to find the area under the curve on the interval from -2 to 7. Use integral notation to express the following limit. So we're just going straight to, we're looking at the interval from -2 to 7, and my function is 3x squared minus 5x, and our variable of integration is dx. And number 4, the volume of a spherical hot air balloon expands as the air inside the balloon is heated. Selected values of r prime of t, the rate of change of the radius in feet per minute, is given in the table below. Use a right Riemann sum with 5 subintervals as indicated by the table to approximate the integral from 0 to 12 of r prime dt. So we need to know our right interval, right endpoint, and our delta t. So this is going to be our delta t, right? Our change in our t here is going to be 2. In this interval, our delta t is going to be 3. There it's 2 again. There my delta t is 4. And here my delta t is 1. If we want to use right endpoints, we're going to start there. So we're going to approximate this as the width times my f prime plus my next width times my right endpoint plus my width times my right endpoint, and we continue on. Now if we do this math, we have 8 plus 6 plus 2.4 plus 2.4 plus 0.5. And if we add all this up, we get 19.3. Using correct units, interpret this in the context of the problem. So this is during the first 12 minutes, because we're going from 0 to 12. The radius of the balloon, because that's what we're finding again, right? The r sub t, or r prime of t, is the feet per minute. The radius of the balloon grew by 19.3 feet. If you have any questions, I look forward to seeing you in class.